Good afternoon, Quantitative Analysis 2 students. This is Mr. Marquetta, and I'm very excited to share with you our first lesson, which is chapters 9.1 and 9.2, associated with limits, continuity, and limits at infinity. Today is July 7th, 2022, and we're in summer session E. Let's begin by talking about the basic concept of a function. In case you forgot, which some of us might have, it might have been a long time since you've seen it. A function generally is an expression in terms of a variable or many variables. For now, we're going to focus on functions in one variable. This particular function is in terms of p. The way we'd say this out loud is c of p. And the parentheses on the left don't represent multiplication. What they mean is c in the specific case that you know what p is. For example, if you knew that p was 9, it would be c in the specific case that p was 9. Then you could go in and put a 9 into every position where there's a p, calculate and find out what c was. You could call it c, or you could call it c of p, but it still is c. You have to look at variables in that way to be able to make it through calc. That's basically what we're doing, friends, is calc here. So first and foremost, let's be familiar with the concept of a function. C of p, or f of x is our go-to. F of x and y are the same thing. And that's a big secret that no one will tell you, that you have to figure out on your own, and I'm here to deliver the goods. When you see f of x, think, oh, that's the y. And every time you see f of x, consider it to be a y. Likewise, today we're going to study limits. Limits are also y values, and it's often confused with whether is it an x or is it a y. Just remember my mantra in your mind. A limit is a y value. And if you keep that in your mind, then limits are going to be easier than you think. Every time you answer a question about a limit, you're giving a y coordinate number. Okay, so let's start by getting our feet wet a little bit with limits. How do limits work? What is a limit? Well, what is a limit in reality? So you can go 65 miles per hour on the Parkway down in South Jersey. That is the speed limit. Now, I don't know about you, but I do like 80, right? Okay, but that is, of course, breaking the limit. Right. And what actually does it mean, 65 miles an hour? What does that really mean as a speed limit? That means you may not go 65 miles an hour. You can go 64.9999 miles an hour, but the limit is 65. Some people would argue, oh, well, I can go 65. And technically, by the mathematical definition, you kind of can, you kind of can't. It's kind of a cloudy area, but ultimately, you certainly cannot go 65.01. That is breaking the limit. Okay, so then ultimately, what do we mean by limits? Well, a limit is what it would be if you could get there. Like, you're not breaking the law if you're on the Parkway doing 60 or 55 or 63, right? So there's a wide range of numbers that are there that would be legal before you get to that limit where you're suddenly breaking the law if you go beyond 65 miles an hour. I want you to think about how it would be in your car to increase your acceleration and to carry on forward until you get to that point of 65. And then when you get to 65, that's when you pull off of the gas. That's something that we have to be comfortable with because that's the very idea of a limit. So let me read the definition. And as I read the definition, take it with a grain of salt. I'm going to be reading a lot of very quirky definitions in this course. And when I read it, please know math speak is kind of hard to digest. And I am going to really kind of analyze and pull apart this whole conversation for us. But first, let's just read it cold, okay? It says, let f of x be a function defined on an open interval containing c, except perhaps at c. Okay, f of x is a function. That's what that all means. And then we have this funny statement. I'm going to zoom in on it. All right. I want you to focus with me on how you're supposed to recite this out loud, friends, okay? You're supposed to say, this is the limit as x approaches c of f of x. That equals capital L. So I'm going to repeat that for us, okay? Because it's a funny wording, but the way you read this out loud is the limit as x approaches c of f of x. This time it's f of x. Next time it'll be a funny expression in x, but that's how you're supposed to read that out loud. Now, this limit, it does exist if you can make values of f of x as close to L as we desire by choosing values of x sufficiently close to c. So when the values of f of x do not approach a single finite L as x approaches c, then we say it does not exist. That's a mouthful and it's hard to digest and understand. Believe me when I say when you start to see pictures and graphs, namely these right here, we start talking about what limits are and how to interpret them, you'll be able to go back to that conversation, and you'll be able to go back to that, and you'll be able to go back to that definition. I'm sorry, friends. You'll be able to go back to that definition, and it'll make a little bit more sense. So let's start by taking a look at these. I'd like to introduce you to three characters in my story. Okay. My story has three different characters. The first character is going to be f of x, which is this thing here. My next thing is going to be g of x, which is this thing here. And my next thing is going to be h of x, which is going to be, I'll make it purple, this thing right here. Right now, let's focus together on this statement right here. Find the limit as x approaches 2 of f of x, and find f of 2. Let's forget about limits for a minute. You understand what f of 2 means. F of 2, remember f is a y value. F of x is something y, right? F of 2 means the y value when x is 2. So what is the y value when x is 2? Well, I can see right here when x is 2, y is 3. And that is a solid colored in point on my graph. And that is on my graph, it's a solid colored in point. F of 2 is 3 because of this point. Now, what is the limit as x approaches 2? Now, that is a very strange concept as x approaches 2. Well, I want you to imagine all of the different dots on this graph, okay? Here's a dot right here. Here's a point. Here's a point. Here's a point, right? Here's a point. Now, if you look closely, you'll notice the x values are increasing. Like when I was here, the x value is -1. When I'm here, the x value might be like -0.2. Here, the value is probably like 1/2. Here, the value is like 1.1 or something. But do you see how x is approaching? X is approaching 2. It's getting closer and closer to 2. If I continue to get closer and closer to 2 as I approach the x value of 2, and I get closer and closer, what happens is, if I could get to 2, the answer would be 3. Happens to be a dot there, isn't that great? And by the way, it is 3. But what if there wasn't a dot there? That is exactly case B. So let's take a look at case B now. In case B, it's telling you that you're trying to find the limit as x approaches 2 of g of x, which is the blue function. And you want to find also g of 2. So let's start with going back to our 9th grade roots. I know how to find g of 2. Let me look at this function. What is g of 2? Well, notice right here, when x is 2, there is no point. In fact, at the place where x equals 2, there isn't a point anywhere. At least in this graph over here, there's a point up here to kind of compensate for this, you know what I mean? But over here, there is no such point. So what is g of 2? The answer is it does not exist. There is no such thing. There is no such value for g of 2. What is the y value when x is 2? Look, there is none. It's a hole. So we would say g of 2 does not exist. But what is the limit as x approaches 2? Okay, as x approaches 2. Well, that's pretty deep, right? Let's approach 2 and see how that feels. Right now I'm over here at a place of, that came out funny. Over here at a place of like x equals -1/2. Here, x equals 0, x equals maybe 0.8. Here, x equals 1/2. What happens right here? And I'll use a little bit of a, see what I'm doing. What happens there? Well, as x approaches 2, y does approach -1. There is not exactly a value for f of 2. -1 is not the answer to f of 2. But -1 is the answer to what is the limit as x approaches 2. So I want you to compare those a lot, friends, okay? I'm gonna take these dots off and these different things. All right, I'm gonna go back to this. And I just wanted to be really clear. I want you to compare these ideas, okay? Here, f of 2 does not exist. However, the limit as x approaches 2 does exist. It would have been -1. If you were walking on that line and you were taking steps along the line, you would be approaching 2 in the same way that you'd be approaching a y value of -1. So In this case, f of 2 does not exist, but the limit does exist. Now let's investigate the third one. Okay, for this one, it's telling you find the limit as x approaches 2 of h of x. Okay, as x approaches 2, and I want you to focus on this piece of the picture with me, okay? As x approaches 2 versus h of 2. So let's start with the easy question. What is h of 2? Well, there is a solid colored in dot right there. And according to this graph, when x is 2, for whatever reason, the y value is 4. There's a dot right there to show that. So what is h of 2? 4. Just like what is f of 2? 3, right? Okay, so if you see a solid dot, it's easy to find f. But if there isn't a dot, then you say it doesn't exist, like in the blue picture. The other important topic here, and then we'll move on to the next slide, is what's the limit as x approaches 2? Okay, so I'm going to use my spray paint can now, okay? I'm going to approach 2. Here I go. I'm going towards it. Can you see that I'm approaching it? I'm approaching it. And as I'm approaching it, what is the limit? Can you see the limit would be 1? It would be 1. In other words, h of 2 is 4. But the limit as h approaches 2 is 1. And perhaps the most important picture here is the picture of h of x, because it shows the illustration and the concept of how you deal with it when the limit doesn't exist and when the limit does exist versus when the function value exists or doesn't exist. These three questions, I want you to come back and look at these a lot when you're doing your homework, because the answers are all right here for you. And you could kind of investigate them and think about them over and over again. I would have put them up if it was easier to see in a Zoom this picture, but we had to zoom in the picture. But these are all the answers that I just explained for you to make it clear how to deal with the actual value, f of 2 or g of 2 or h of 2. Likewise, the limit as x approaches 2 for the function, and how you can apply them to which one is which. Okay, so example 1 is probably one of the most important examples in your homework to understand when a limit is and when a limit does not exist, and likewise when there's a value for the function or not. All right, so now that we kind of have an idea of what limits are, and it's a funny idea, but they are practical and they do kind of hold merit, especially as you go further into calculus when you start to try to figure out what the derivative is. In fact, if it wasn't for limits, we wouldn't have derivatives. So it's kind of a building block towards getting to derivatives is the point of limits. So using the functions graphed here, determine the limit, y the limit as x approaches 2 does not exist for each. So let's start by thinking about where is x approaching 2. And you could see that we do have here, is a big solid thick line for this. Here we have 2 right here, right? Here we have 2 right here. And here we have 2 right here, right? And what we're going to do is we're going to approach it, all right? Now, when you approach a limit, it's important that you approach it from both sides, from the left and from the right. I'm going to explain why. For example, in this one, I'm going to approach from the left for the first one. So I'm going to use my spray paint can and do some graffiti. I'm approaching it from the right. As I continue to approach x being 2, meaning I'm getting closer to an x value of 2, what's happening to the y values? Are they not increasing forever and ever? The limit is infinity. Or, since infinity does not exist, the limit does not exist. What happens if I approach 2 from the right this way, and I get closer and closer to x equals 2 this way? What's happening to my y values? Yes, again, we're approaching infinity. Depends on who you ask and what college you're going to, but the answer is either does not exist or positive infinity, because infinity isn't a limit anyway. So it depends on who you ask. So for f of x, what is the limit as x approaches 2? The answer is infinity. Now, for g of x, let's approach 2 from the left. It looks like as I approach 2 and get closer to x equals 2, my y values get closer to infinity. In fact, I can see it shooting straight down. In other words, from the left, the limit looks like it's negative infinity. From the right, as I come in towards 2, it looks like my y values are actually getting closer to positive infinity. So notice that as I approach from the left, it's negative infinity. But if I approach from the right, it's positive infinity. If you approach from the left and the right and get 2 different things, then immediately the limit does not exist, and you say the limit does not exist. In the case of the first one, you could argue it does exist as positive infinity because it's the same on both sides. But for the middle one, does not exist. And the reason why is because it's a different value from the left than it is from the right. That's really crucial about determining when limits don't exist. If it's not the same number from the left as it is from the right, that's a quick, easy does not exist, right? And last but not least, let's do h of x. Let's approach h from the left. As I approach h from the left, to get to 2, it looks like the y value is actually 0. We put a 0 here. But as I approach y from the right, as I approach 2 from the right, it looks like it gets to 3 for a y value. This is supposed to be my graffiti 3. Okay. In other words, can you see that again? It's not the same from the left as it is from the right. This is another example of the limit does not exist. Okay. So for all of these, you could explain that it does not exist. In the case of the first one, it does not exist because for both of them, it is infinity. The way that we would say that out loud is, and I want you to look at my writing and right over here, as x approaches 2, and see right there is that little plus. Friends, that plus appears to look kind of like an exponent. I'm looking at what's written right here. It looks a little bit like an exponent. The way you read that out loud is from the right, meaning as x approaches 2 from the right. F of x, or the y value, is approaching infinity. It's going up. As x is approaching 2 from the left, again, the y value is shooting straight up infinity. And yes, they are both the same limit, but infinity does not exist. Thus, the whole thing does not exist. Same thing is happening here with this one. In this case, what's happening is in one of them, you get negative infinity, and in one of them, you get positive infinity, like we talked about. And that's the reason why that does not exist. And last but not least, of course, the third one does not exist as well. And that is for the same reason. As you approach from the right, you get a different value than as if you approach from the left, 3 and 0. All right. So we like to call these one-sided limits. And sometimes if you see the limit written with x approaches a number, you might see a little plus or a little minus there to tell you, well, tell me what the y value would be if you came from the right. Or tell me what the y value would be if you came from the left. In other words, sometimes a little plus or minus in there changes whether it exists or not. For example, if I had changed this one and said, can you tell me the limit as x approaches 2 from the left? Okay, there's an answer, it's 0. What is the limit as x approaches 2 from the right? Yeah, there's an answer, it's 3. Okay, but notice that as we come from both sides, they're not the same, so there's no limit. Now, you guys might remember me saying yesterday when we met in class, this is not hard stuff. It's just weird stuff that we have to talk about. You're going to have a lot of cases of beautiful, interesting looking graphs that are different curves and all kinds of weird, these are hyperbolas. One of them is a piecewise. You'll have all kinds of funny looking algebraic functions and graphs. And you'll be asked questions about the limit from the left and the right and such. And that practice in web design is going to get you real sharp and ready for your exam, because those are the kinds of questions you see in your exam. Right. One other thing that's kind of important, the limit as we approach from the left is not equal to the limit as we approach from the right, and that is the primary reason why the limit does not exist. All right, so let's talk about properties of limits. Now, I want you to consider limits as if they were, oh, wait a second, there we go. I want you to consider limits kind of like the way you would deal with logs or exponents, or sine, cosine, and tangent. There are little rules about them. And there's like a list of rules, you see them here, that you could apply to algebraically simplified, very complicated limits. Or likewise, if you have very complicated limits, or if you have very easy limits, you could exaggerate them and make them into bigger expressions using these concepts as well. So what's the idea? Well, the easiest and most important idea here, the limit of a number is just that number. The limit of 3 is 3. What does it really mean? It means if you graph y equals 3, the limit as x approaches any number is always going to be a y value of 3. What does y equals 3 look like? Let's talk about that for a minute. This is if you don't remember. A lot of people don't remember this kind of stuff, but I'm just going to give you a quick little drawing. All right. We're doing I'm going to talk about y equals 3. All right. Y equals 3 is a simple line at the place where y equals 3, like this. That's y equals 3. Now, if x approaches 7, like right here, guess what the y value is? 3. If x approaches negative 91, guess what the y value is going to be? It's going to be 3. And if you can believe that for any y value, y equals 3, y equals 21, y equals -9, y equals 5 pi, whatever. If you make it that, remember that if we say the limit is the y value, what is the y value when the function is just y equals k? Because remember, friends, this is a function. K is a number like 3. So it's like y equals 3. The same thing here. If you were doing a case where you're approaching a value and the function was just f of x equals x, then immediately the answer is just going to be, clear this, sorry, it's just going to be the thing you're approaching. So here you have the concept of as x approaches 9, f of x equals 9. So when you get to 9, you're gonna get 9 is your answer. What does y equals x look like? Remember, this is a function. This is y equals, this is a function. Y equals x is a function, if you may recall, looks like this. Here's your xy plane, and here's y equals x. It goes straight through the middle on a perfect 45-degree angle. It's also called the identity function. You may have learned that in Algebra 2 or pre-calc. In this situation, y and x are always equal. If f of x equals x, that means the points are 5, 5, 9, 9, 3, 3, 70, 70, right? So y equals x, or f of x equals x, means just that. So if x approaches c, like x approaches 13, well, the y value is going to be 13. If x approaches -77, guess what the y value will be there? It'll be -77. So in summary, the way you interpret it is the limit as x approaches c for just x is going to be just c. Okay. Next, if you're adding two functions together, okay, you might as well just take the limit of the first one separate and then take the limit of the second one separate. Also, by the way, if you were subtracting or adding them, that still holds. See the little plus or minus? The reason that's there is because if it's a limit of this function plus that function, it's almost like the distributive property. You can distribute lim to each of them and do them separate, is the point. Or if it was minus, same thing. If it was, for example, limit of x squared minus 10, you could do the limit of x squared, find out what that is, then find minus, then do the limit of 10, and find out what that is. So you can, it's almost like the distributive property, but it's really not. It's a limit property, and it's specific to the concept of limits, not multiplication and distribution, right? There are other ones associated with multiplication, as you can see here. If you're multiplying them, you could do them separate and multiply your answers. If you're dividing them, you could do them separate and divide your answers. And if you're rooting them, you could do it separate and then root it later. Okay, let me repeat that one because that one's a little bit weird. Say you were trying to figure out the limit of the square root of some funny function. Forget about the square root and just find the limit of the function. Then when you're done, make sure you take the root of your answer, is the concept. So look at these 6 rules. When you're doing algebra with a pencil and you're trying to write these things and you're trying to figure them out, and I do recommend you get a pencil and a paper for this kind of stuff. It's going to be the kind of class where you're going to be trying to write things a lot. We want to be comfortable with these little rules about limits. And when you're doing simplifications or exaggerating them, make sure you come back to our video and watch this again. Or make sure that you come and look at this PowerPoint and check to see if you need to remember the story of multiplying them or dividing them or rooting them or whatever. Okay, so these are some great ideas, and we're going to keep on referring to this today while we're doing simplifications. All right, let's talk about 2 important functions. This is a little bit more of a macroscopic algebra concept. There are many kinds of functions, but we're going to focus on 2 specific kinds of functions today. The first one is called a polynomial function. The second one is a rational function. Let's talk about these words and think about what they mean in our language. What does polynomial mean? Poly means many, like polytheism is a religion with many gods. And then we have nomial, which means numbers or names. So polynomials are those beautiful functions that you're so familiar with. X squared plus 2x plus 10, 5x to the 10 plus 5x to the 4th. If you look here, we're giving you oops, come back. If you look here, we're giving you a kind of template of what they should look like. That they always have first, the last one is going to be a coefficient, a simple constant number, right? And then the one behind it is just a coefficient in x, and then it's going to be another coefficient in x squared, and so on until you get to the highest power, which is x to the n. It might be the 5th or the 20th or whatever the highest power is, with its own coefficient, and everything carrying on from that. In the case that you have like x cubed plus 1, that's really x cubed plus 0x squared plus 0x plus 1. So every polynomial can be fit into this template. And in general, a polynomial function has this kind of a format. There are a lot of really easy judgments you can make just knowing that your function is a polynomial function. You can make statements about limits without having to think very hard at all. That's why, friends, it's so crucial that you're able to recognize when things are polynomial functions and when they're not. Likewise, we have this other idea going on of a rational function. This is a rational function here. Rational functions are basically polynomial functions, just one on top and one on bottom. That's all. And there is a division going on. In the case of that division, you want to just make sure that you're not dividing by 0, because once again, always dividing by 0 is the biggest sin of all in mathematics. But if you are able to, you should be able to put the numbers in both positions like so. All right, now let's see if we could put this into some practice and make some sense of this today. First, let's focus a little bit more on that rational function. By the way, why is it called rational? Why is it called rational? Okay, I want you to think for a minute about the word rational. Doesn't it look kind of like this word? And this word? And this word? How about this word? Those words all mean the same thing. They mean divide. They all mean divide. Ratio is a comparison of two numbers using division. A rate is usually in the form of a percentage, which is ultimately always a division of 100. Rations are when we have all of the foods and we have to divide them amongst the soldiers. Fraction is the most explicit form of division, right? So what are rational expressions and rational terms? Rational functions. A rational function is a function that has a big old division line, like you see there. Maybe it's x squared plus 1 over 2x minus 9. You know, whether it's like there's an over in it. That's what rational means. Okay. So, starting with our conversation about rationals, when you try to solve a limit, the most direct and easy way to deal with a limit is to just plug in the number straight. And if you plug the number in straight, the way you would to a function, you'll get a simple answer of a number, and it feels like you're doing basic arithmetic. And ultimately, that is the answer. The concept is that you should be able to look at a graph and try to think of what it means to approach a number and so on and so forth. And you may have noticed when we were in this position earlier. Come back. When we were in this position earlier, not this one, that you think, well, wait, aren't limits just the same? Now, these are the very strange, odd cases where the limit is not the same as the function value, but usually it is. Only in strange cases, because how many functions have you seen like g of x and like h of x with a hole in it like that? You don't see that until you get to calculus. So the way you want to look at limits then, guys, is look at them like they're functions. It's not written very closely here, but I'm going to put it like this. If you have the limit as x approaches, say 3, all right? And then your function is something like 5x minus 1 minus 2. The typical example, just put 3 in there. 5 times 3 is 15. 15 minus 2 is 13. So what we're trying to say is generally when you're doing limits, almost always, you could just put the number right in and substitute like it says. If I was saying find f of 3, you know how to do that. Okay, it's 15 minus 2, it's 13, right? So when it comes to finding limits, usually the first thing I want you to do is take the number you're approaching. For example, x approaches 3. Take 3 and put it right in and see if you get an answer. Sometimes you won't, and if you don't get an answer, then you're in an intermediate form, indeterminate form. Let's take a look at those indeterminate forms now. There's 2 types. The way I want you to look at this, guys, is that there's really 2 types. In the first case, where is it written? Oh, actually, it's right here in the title. I put it in the title. Good place for it, right? First of all, you might get 0 over 0. So like If the limit of the top is 0 and the limit of the bottom is 0, then when you divide them, it's like putting 0 over 0. So the only way you could deal with it is to try to play around with algebra to see if you could cross something out so that maybe you don't wind up with 0 over 0 anymore. Likewise, here we have a situation where we have a over 0, meaning once in a while you'll find a rational function that the top thing, f of x, does not give you a number 0, but the bottom one does. That's what that's saying. And if that happens, then we just simply say straight out, it does not exist. That's it. You don't even think about it. You don't have to put any numbers in. You don't have to try to do any factoring or do anything like that. If you find that the top is a number and the bottom is 0, then it does not exist. Once in a blue moon, you might be able to factor and cross things out so that you don't have that 0. But remember that if you have a number over 0, it does not exist. Now, in that breath, let's say we did our work and up here we found a 0, but down here we had like 15. 0 over 15 certainly does exist. If I had nothing in my hands and 15 of you got to share it, would there be an answer? Yes, you'd all get 0, wouldn't you? Yes. So you have to remember that 0 divided by a number is just fine. It's 0. But a number divided by 0, that's where you get a problem. So sometimes you'll be doing these questions and you'll see an indeterminate form that brings you to a position of 0 over a number. It's not indeterminate. It's not indeterminate at all. That is 0. 0 divided by a number is 0. But if you have 25 over 0, that's indeterminate. So how do you deal with it? Just factor it as best as you can. And if you can cross things out and do it again, then maybe you can get an answer. So in a very mean way, that old ghost from algebra is coming back to haunt you here in calculus, factoring the F word. So let's take a look at some of these questions. The way that you deal with it is you put the number in just the way you see it and hope for an answer. If you don't get an answer, then you have to play around with factoring and hope that something knocks out to the point that you get an answer. So first of all, let's look at example 3. Okay, in example 3, we're asking you to substitute directly in their -1. So it would look something like this. Oh, I can't see that. I guess I better put it in white. Put it in red. I guess red is good. All right, let's go do that work, calculate that, right? And what do you get? Let's see. Well, looks like this right here, -1 cubed is going to make -1 again. This right here is going to be -2. -1 minus -2 is like -1 plus 2. And as you can see right here, -1 plus 2 certainly is 1. Our answer is 1. All right. So example 3a is a great case. And hopefully every time you ever look at a limit, it's that simple. You put the number right in, just like it's a function, do a little arithmetic. The answer is 1. All right. Next, let's take a look now at the next one. When you put 4 in there, what happens? Can you get an answer? Sure you can. It would turn out looking something like this. It would be 4 squared minus 4x, and x is 4 this time. Let me just put my 2 up there. And then I have a line. Give me the line. And then I've got the bottom, which would be 4 minus 2. All right. Simplify. On the top, we get 16 minus 16. On the bottom, I have 2. What is 16 minus 16? Oh, yes, it is. It's 0. Do we say that the limit does not exist? No, not at all. What is 0 divided by 2? Is there an answer? Yes, it does exist. It's 0. Answer is 0 to that one. So here we go. For 3b, oops, our answer is going to be actually 0. Okay. Example 3 is great because we want to always go back to example 3, hoping that every question is like example 3, where you simply put the number in, you get the answer, boom, you're done. Example 4 and example 5, now you're going to see the case of the indeterminate form that we talked about. In the case of indeterminate form, what happens is you start by plugging the number in. You can plug the number into the whole thing if you want, but really what you're looking for is there a 0 on the bottom? Because if there's a 0 on the bottom, we got a problem. And if you look closely here, you'll see in the case of, oh, sorry if I'm trying to get there, it is. In the case of the limit as x approaches 2, when you put 2 right there, what happens to your denominator? Doesn't it collapse? It becomes 0. You're like, oh, now what? Also, it happens here. Take a look. Happens here. In the case that we approach 1, in the bottom, if I put 1 in there, I get a 0. Likewise, it just so happens to be true that if I put 1 here, I also get a 0. And in this one, if I put a 2 in here, I also get a 0. Which means, in other words, both of these have the indeterminate form 0 over 0. So your first gut reaction would be, oh, I guess the limit doesn't exist, right? But it does. It does. And let me explain why it does. Whether your algebra panned out or not, if you graph this thing, x squared minus 4 over x minus 2, and look at it and approach 2 in the same way we did way back in example 1, you will get an answer of 4. 4 is the answer. Why did it turn out algebraically this way that I get 0 over 0? Well, math and calculus is kind of funny, but here's how you handle it. Every time you ever get an indeterminate form like 0 over 0, please do not just assume that the limit does not exist. Instead, it's time to do some factoring. And I know you don't want to do it. And I know you got a block. So I'm going to ask you to try to look into it and make sure you learn how to do factoring. If anyone has issues with factoring, I can go over some great examples from algebra class back in high school. Also, chapter 0.6 in our textbook has a whole thing about factoring, so you could go and do practice there. Likewise, you could always, of course, go to YouTube and type in factoring and watch all kinds of videos about factoring to get yourself familiar with it. But please be forewarned, friends. Don't think you're going to make it through calculus without doing factoring. You need to know factoring, okay? So you may recall this first one. This first one does pop out. It's one of the easier kinds. This first format here is a case of difference of two squares. The way difference of two squares worked was, and I'm gonna pull it up so that I could show you just what it looks like. Here we go. All right, let's share this. Here we go. Let's share this thing. Remember this monster? This is called difference of two squares. So if you're trying to factor and you see that you're subtracting two things and they're both able to be rooted, like x squared minus 9, right? Or even anything even, like y to the 10th is the perfect square. It would be y to the 5th, Basically what you do is you root each of them. You root this one, whatever it is. If it was 9, make it 3 and 3. Likewise, you root this one, whatever it is, put that here and here. And then don't forget to do plus and minus, and you factored it. If you go back and do the FOIL method, remember FOIL, where you go like this, first, outer, inner, last, it'll boil down to a squared minus b squared, okay? That in mind, let's carry on now with this question. In this question, you'll see right here, this is a difference of two squares. The square root of x squared is x. The square root of 4 is 2. So if I do x minus 2, trying to write with a mouse, so please excuse my chicken scratch, okay? And then, of course, we'll write x plus 2. That's what's going to go right there. So doesn't this happen? This goes away with this, doesn't it? So now, this has just turned into the limit x approaches 2 of just x plus 2. Horrible handwriting, Anthony, horrible, right? And if it's just x plus 2, then if x is 2, what's 2 plus 2? And that's why it's 4. So I think you can see the point is that when you have a function, I'm sorry, not a function, when you have a limit and you substitute in the value, if you get an indeterminate form, you must try to factor it. And after you factor it, usually they're set up to collapse that way when you factor them, that things will slash out and you won't have a denominator anymore. You're now trying to find the limit as x approaches 2. The answer is 2 plus 2, which makes 4. The same thing happens here. This one, oops, Let me get rid of that stuff. This one here is an example of a basic trinomial. There's basic trinomial factoring and advanced trinomial factoring. There's a couple of ways to do this. The best way to do it is guess and check, but there is something called the Berry method that you may have learned about. I'm going to open that up and show you that as well. Let's see if I can get a good Berry method example. Hold on, friends. This one's okay. Let's look at this one. All right, I don't know who wrote this or where this came from. Okay, but basically, this is the concept of the Berry method. The way the Berry method works is you figure out the first number times the last number. In this case, that would be 5 times 36. And then, this is not a really good example either. If you do 5 times 36, you get 180. And then you think of all the different ways that you could multiply to make 180. These are all the ways you could multiply to make 180. One of them is going to work such that when you add the two of them, you get negative 36. It's this pair. And that's why your solution looks like this. And now you do a little distributive property or a GCF, and then you just group these. Now, the way I'm saying it, it's like, oh yeah, what a piece of cake, right? I mean, this is a lot, you know. This one has a coefficient of 5 in the front. This is an advanced polynomial. Let's take a look at a basic trinomial. All right, I like this one. We're going to look at this one, right? All right. So this is the idea that we're trying to factor. First, what you do is you say to yourself, what could go here? And what could go here? Well, to make 2x squared, I'm going to put 2x and x. And then to make 10, I could put like 5 and 2, or maybe I'll put 10 and 1, or maybe I'll put minus 10 and minus 1, and you experiment and keep doing FOIL until you get it to come back to 2x squared minus 9x plus 10. These are all great cases because they'll help you. However, still, they're not the most basic. There is a trick to a basic one. I really do want to show you that. Let me try that one more time. Maybe a equals 1. This is what I wanted to show you. All right, let's go here. So in this situation, you'll notice this models our picture very well. It's x squared plus a number, x plus a number. The way you're going to handle it is you're going to start with the last number, 20. And you're going to think about all the different ways you can multiply to make 20. Here they are. You can do it at 20 times 1, 10 times 2, 5 times 4. I think that's just about all of them. Do any of those add up to 9? Yes, 5 and 4 do. So what we'll do is we'll write for the x squared, we'll put x and x. And for the 20, we'll put 5 and 4 here and here. If you multiply this together, guess what you'll get? Thing back. So now with that in mind, okay, and let me just review once more. Starting with x squared, not 5x squared, starting with x squared, you take the last number. What two numbers multiply to make that number? Which pair adds up to the middle term? And then those are the two numbers you'll use in your factoring. This time, 5 and 4 are the numbers that work to make 20 that also add up to 9. So we're going to say x plus 5, x plus 4. And if you multiply it back, in your mind at least, look at it and squint your eyes and scratch your chin and say, does that make x squared plus 9? And it does. So you know what you've written is still sound and it's still the same quantity. Right? Now, let's go back and look at our PowerPoint. Okay. And here, if we try to factor this thing, we're going to ask you to find two numbers that multiply to make 2 and add up to negative 3. Those numbers are negative 1. I'm typing it. I can't write it. It would be x minus 1 and x plus x minus 2. Like so. And I know that because I experimented with all the different ways I could multiply to make 2. Of course, the first idea is 2 times 1. And then you might say to yourself, that's it. No, there's -2 times -1. And plus, don't forget, our goal is to add up to -3. So -1 and -2 multiply to make +2 and add up to -3. That's why that's the appropriate factoring. And likewise, on the bottom, I have factoring to do again as well. Down here, x squared minus 1 is your age-old difference of 2 squares case, which will boil down to something like this. X minus 1, x plus 1. And what I'm going to do, friends, is I'm going to put a line in there. All right. And can you see that these knock out? And now we're only left with this. X minus 2 over x plus 1. So put your 1 in there. So we would do 1 minus 2, which is -1. And we do 1 plus 1, which is 2, right? And see what our answer is. It's -1/2. So at a first glance in example 4, both of these limits appear to give no answer because they're indeterminate. And when you get indeterminate with 0 over 0 or with a over 0, like we'll see in example 5, you must do factoring to the fullest extent and then see if you can cross things out. Usually after you cross things out, you're able to solve the limit. All right. Now, let's talk about example 5, which I have on the next page. In example 5, the same thing happens, except you don't get 0 for the top and bottom, you just get it for the bottom, which is more than enough. So if that be the case, noticing that when we do put the number in, x is approaching 1, here we get a value of 0. Let's see if we could go ahead and factor this. And if we do factor it, can we cross things out? Well, the top, I'm going to factor the top. I'm thinking of 2 numbers that multiply to make 2 and add up to 3. Shouldn't that be 2 and 1, right? So I have x plus 2, x plus 1 on the top. And then on the bottom, as you could see, I have x minus 1. Right. Sometimes students get a little bit confused with that x minus 1 action. Just remember, if you want, you could just put it in parentheses 2. It doesn't hurt. And then it does make a lot more sense. Oops, wait a second. And then it does make a lot more sense to be able to cross them out. But if you look closely, they don't really cross out. Was I sure about x plus 2 and x plus 1? Yeah, that is true. It looks like it doesn't cancel out. What do I do now? Should I just say it does not exist? No, you can't do that. You have to find an alternative way. So what we're going to do is we're going to talk about something called tabular analysis. It's a very fancy word for using a table to analyze a table. Let's literally approach 1. Literally approach it. If we're going to approach, if x is approaching 1, let's pretend x is 0.5 for a minute. Then let's pretend it's 0.7. And let's pretend then it's 0.9, and then it's this, and then it's this. See how I'm approaching 1? I'm approaching 1. And every time I approach 1, look what happens. I put 0.5 in, and it spits out this value. I put 0.7, and it gives me this. I put 0.9, and look what's happening to y. In other words, what's happening to the limit. As x is approaching 1, the limit is approaching infinity. Or actually negative infinity, isn't it? Because they're negative values. Negative infinity. And if you do it from the right, you wind up approaching positive infinity. What do we mean by approach from the right? Well, if the number we're approaching is 1, and you're approaching it from the right, that means you're starting by thinking about numbers above 1 and coming down toward 1, like 1.5, and then 1.2, 1.1, 1.01, 1.00. Look how very close to 1 we are, and look how much closer to infinity we got. So if we were able to get to 1, then we would be able to touch infinity, but we never will get to 1, and the limit doesn't exist. The reason why the limit doesn't exist is really because both of them are infinity. Whether one is negative and one is positive or not really is not even that important. What's important is that both of them are infinity. That alone is it does not exist. All right. So tabular analysis, we're going to talk about that too, how you do that. We're going to use Desmos to do that. All right. And we're going to take a break though, because I've been barking algebra at you for 50 minutes now, and I don't want you to get bored with my class. So friends, let's take a short break. Okay. Right now it's 5:22. You're mine until 6:45, but I won't hold you that long. Don't worry. But we do have a little bit more that we have to go through. We're going to do tabular analysis now using Desmos. So let's take a little break. Right now it's 5:22. Friends, will you please join me again in 15 minutes? I'd like to meet again at 5:37. To be kind, let's make it 5:38. Okay, so if I'm going to pause our recording, and at 5:38 we'll return. Coming back from our break, I'd like to share with you now how to use tabular analysis in Desmos. Desmos has a lot of great functions in it. We use it a lot in quantitative one, those of you who are in my quantitative one class. It's basically a graphing calculator for a computer. So instead of going and buying a new calculator, a graphing calculator, we're going to do all of our stuff online using Desmos.com. Today I'm going to bring you to Desmos.com, but first I want to give you a little bit of a explanation using this particular slide. You'll notice Desmos has little windows where you could put things in. You're going to type in a function, as you could see right here. You'll just type in a function, and then when you do it, there's a place over here, edit list. Okay, and you click that. It's a gear. Usually it means settings, right? And then this little menu will open, and you're going to choose this right here because this means please let me have a table. So let me break it down. That means you could put any function into Desmos and then put any x value in, and it will quickly calculate easily for you. For example, what about if x is 0? Oh, it's -2. What about if x is 0.5? It's -7.5. It's right there. You could put them in and just get any value you want. I'm going to show you that right now. If you are able, I'm going to ask you to follow along. Okay, go ahead and open up any web application. Could be Google Chrome, or it could be Firefox, or Safari, or Edge, or whatever. And then when you are in there, you're going to go to Desmos.com like this. Okay, Desmos.com. And then there's a place for you to sign up or register if you want, and you can if you want, but you don't have to. You can always just come here. It's always free. It's a graphing calculator. And then let's type a function in here. Let's start with an easy one. How about y equals 3x minus 1, whatever. You could put cosine in there, logarithms, any kind of crazy rational functions, exponents, fractional exponents, all kinds of anything you want in there, cubics, square roots, all kinds of roots, all the math stuff you can dream up. You can make any function up you want, and it will give you a nice graph. Likewise, after it gives you a graph, you're in a position to come up with any points you want. So I would first click in the window of the graph. Then you click the gear, like we said in the PowerPoint. And then after that, you click the little table, and a table appears. Here are some examples. These are the most common examples. Notice on the line, you have a couple of dots showing to illustrate those points. But if you wanted certain specific points, like 0.1, 0.01, 0.001, and you can't see them here, but if you zoom in, you'll see them zooming in more and more, right? So Desmos is a really strong tool. It's really helpful when you're doing these calculus things, and in particular, if you're trying to approach. So let's say, for example, we were finding the limit as x approaches 0 or something like that. Well, I could, I could get rid of all these, or I could start fresh. I'll just skip a line. Maybe I'll put in there, I'm trying to approach 0 from the left. So I'll put negative 0.01. And I'll put negative 0.001. I'm closer to 0 now. Negative 0.0001. I'm even closer to 0 now, right? And look at what's happening is I'm getting even closer and closer to -1 is what's really happening. So this is the idea of a limit, is that you consider what it is like at stages toward a specific value. As you change x, what is happening to y, and then ultimately, if you could get to where the limit is approaching. What would y get to? That's the answer to what the limit is. And once again, don't forget limits are y values. That's an easy thing to confuse when you're doing math here, is thinking, oh, I got the point. It's 5, 7. So the answer is 5. No, in 7, the limit is the y value. So just remember the limit's the y value. That's another little tip that'll always kind of come in handy. All right, so we should be able to do tabular analysis then. Let's do an example using tabular analysis now. I'll go back to our lecture. And here we have an example that's a little bit more abstract than mathematics. You'll see some questions like this in WebAssign, so I just wanted to prepare you. They're the general idea of what it means to do a limit. There's not even really math particularly in this. Let's read it and I'll explain what I mean. USA Steel has shown that the cost C of removing P% of the particulate population from the smokestack emissions of one of its plants is this function. And we see it's C equals the function in P. Investigate the cost of removing as much pollution as possible. So one thing we have to think about is, in an abstract way, as much as possible in terms of P% kind of means approaching 100%. So think about that expression, as much as possible. Removing as much pollution as possible means, wouldn't it be great if I could remove 100%? And maybe I can, but even so, I'm going to talk about as much as I possibly can, which is more so the limit as I'm approaching 100 is what we're really talking about. Now, if you're able to read this word problem and interpret it to say, oh, I know, they mean the limit as P approaches 100, then, you know, the only reason I'm bringing it up is because you'll see questions like this in WebAssign, and try to remember when it comes to percent and P, the application concept is that you're approaching 100. So if we put 100 in here, ultimately what would happen is we would wind up with something that is unbound. Imagine for a minute putting 100 right here. On the bottom now you have 100 minus 100, and of course now you have 0, right? And you can't get an answer to 0 because of course you can't divide by 0. So even though the top is 0, because oh no, this top is not 0. I'm sorry, P is 100, so the top would be 7,300,000, right? But or 730,000 is actually what it would be. But the point anyway is it's a number over 0. It's not 0 over 0. It's a number over 0. Either way, that is an indeterminate form. Notice that you cannot factor this one. Even if you tried to think about what it would be like to factor it, you really can't. That is something in math that I know a lot of students will look at something like this and it'll boggle their mind a little bit. You go a little cross-eyed thinking, can I factor it? Can I factor it? What can I? You can't factor this one. That's okay, you can't factor this one. But the concept is, if I could get to 100, then it would be a huge, huge amount. So if it was 730,000 divided by 0, it's an unbound. If you graphed it and took a look at it, or if you did tabular analysis and took a look at it, you'd see that the figure just continues to escalate and escalate toward infinity. We see things like that also when we do when we do the next question. You'll see something like that. Ultimately, the answer is it would be cost prohibitive to remove 100%, meaning it would be all the money in the world and more infinite money. So in the same way that you have 0, you know, the opposite of nothing is everything, and the opposite of 0 is infinity. So if you're taking the limit of something over 0, the answer is it doesn't exist, it's infinity. Let's do it with tabular analysis and you'll see what I'm saying. The function is 7,300p over 100 minus p. In Desmos, I'm going to clear what I just did. I'm also going to click home over here. And I'm going to change the variables so that they're y and x. Y equals, all right, 7,300 x, and then over. You could get over with just type in the slash. It turns into fraction for you. And then you'd write 100 minus x there, right? Just confirm that that's correct. Yeah. Okay. Now say I wanted this as a table because I'm going to do tabular analysis to get this limit. So I would make sure I'm clicking on the box. Okay. It's a funny looking line, but that doesn't matter. I could click home to get back to the original or origin in the center. And let's get a table now. And we'll put the table in. Let's try to approach 100. All right. At 80, the figure is 29,200. At 90, the figure is 65,700. At 99, it's 772,700. Now you're getting close to 1 million. Let's do 99.9% of the pollution. Look how humongous the number is. That number is in the millions. It's 10 to the sixth. What if we get even closer? 99.99999. Look at what happens as I type nines. So what's happening as I'm approaching 100 for x? Y is approaching infinity. And ultimately what it's trying to say is, the closer you get to 100, the more money it's going to cost, is ultimately the story. And that's why the answer in an application, spoken in terms of an application, is it's cost prohibitive to remove 100%, meaning no one can afford to remove 100%. And of course, it is a grim tale about pollution as well. So that's example 6. And try to remember, friends, when you see P and you're approaching with a percent, you're usually approaching 100 in the limit. All right. Here now we're going to talk about evaluating limits. Here we have a piecewise function. A piecewise function is many functions that were like cut with scissors and then slapped together on the same plane. Here we have two functions. One of them looks like a parabola, x squared plus 1, and I'm sure you recall learning about that when you were in school. If x squared is there, it's a parabola. That's only from 1 and back. So it's x is less than or equal to 1. If x is less than or equal to 1, the picture looks like that parabola. That's to the left of 1. And it looks like x plus 2 if x is to the right of 1, meaning the straight line x plus 2 is just a plain diagonal line. Let's take a look at that picture. We could graph it in Desmos using this syntax. Notice in the syntax here, we're using fancy brackets. Those fancy brackets you might have seen before if you were ever studying set notation. And likewise, we have colons here. Take a look. You're using a colon and a comma. And then once again, a colon. So using those syntaxes just perfectly and carefully, you can construct piecewise functions as a single line of syntax writing in Desmos, and it'll give you a perfect picture of it, as you can see, like we imagined, at the place of x equals 1, which is right here. Okay. We have to the left of it is the parabola, and to the right of it is the linear. Okay, so now we're asking questions about limits. Find the limit as x approaches 1 from the left, and as x approaches 1 from the right, and then in general, just of 1. So if you're approaching it from the left, and I'm going to get my spray paint can out again. If you're approaching it from the left, that means you're coming in from this direction here. From the left, right? You're coming in, like the x values are negative, now they're 0, now it's maybe a half, now it's 1. So as I'm approaching 1, what is the y value that I see there? What is the y value? And the answer to what is the y value, it's going to be the point 1, 2 right there, right? Let's draw a point in there. There's the point, and I'm going to call it 1, 2. So what is the limit then if I approach from the left? 2 is the limit. Remember, limits are y values. Now, let's come in from the right, because they're saying now find the limit as x approaches 1 from the right. So if you're coming from the right, I'm going to get my graffiti out, my spray paint can, and I'm going to go ahead and start coming from the right. Right now, I'm like at x equals 2.5, x equals 2, x equals maybe 1.5, right? And now here I am finally at x equals 1. What is the y value there? What point is that right there? Let's give it a point. There's a point right there. A bigger one. Okay. And what is that point? Looks to me like it's 1, 3. Remember the language. As x approaches 1 from the right, the limit y is approaching 3. The answer is 3. So coming from the left, the limit is 2. Coming from the right, the limit is 3. What about the limit as x just approaches 1 with no specification about left or right? The answer, it does not exist. And look closely right here in our answers. It doesn't exist, and you might remember why. We explained earlier, because as we approach from the left, it is not equal to what it is as we approach from the right, and it has to be in order for it to exist. Here in this case, it does not exist because they're two different values. Okay, so we should be able to find limits for functions approaching from the left or right, not only using a graph. I feel that the graph is the easiest way to see it, but also using a table. You have to be able to use tabulature analysis to be able to come in from the right or come in from the left, getting closer and closer. Using the best way to do it is using place values like 0.1, 0.01, 0.001, and such like that. And that's how you can get closer from the left and from the right. All right, we're gonna do a couple more cases of tablature versus algebra versus graphing also before we leave today in a couple of examples. So here, I've brought up once again all of the important properties of limits. There's 6 little axioms or theorems there. And don't forget the story about the indeterminate forms of 0 over 0 and also, of course, of a over 0. And what we'll do is we'll take 2 examples of limits here. Good news, we have the answer already. For A, the answer certainly is 3. For B, the answer is does not exist. And we're going to ask you to please try to find those answers using a graph. Then find the limit using numbers or a table. Numerically means tablature or tabular analysis. And then, of course, algebraically, which means maybe factoring and slashing out. All the different things we did today. For A and B, the answers are 3 and does not exist. Let's talk about graphically why those are the answers. The way I would do that is I would take this part of the limit right here, and I'd say y equals this in Desmos. Take a look at it and try to approach 5 with that. That is a 5 there, isn't it? Yes, limit as x approaches 5. And it must approach the same value from the left as it does from the right in order for me to claim what it is. So let's go take a look at that. I'm going to put this function into Desmos for us now. We'll close this. And we're going to come back. Okay, good. And then I'm going to go get that function. Don't forget to write y equals. It's a very common mistake when you're playing around with Desmos to forget to write the y equals. All right, x squared plus 2x minus 35. Oh, it's x squared plus, sorry, plus. And then over. And by the way, when you have things like this, you could put them in parentheses to get the whole thing over. Because if you don't, when you type 35, it'll just go and do the 35. So I use parentheses and it goes over the whole thing. Now the denominator is x squared minus 6x plus 5. Oops. Plus 5. Okay. So as you can see, it's a beautiful hyperbola. This is something we call a hyperbola. It's one of the 4 conic sections. Conic sections are circle, the hyperbola, the parabola, and the ellipse. You learn them in pre-calc, or you might learn them in calc. Here we have a function anyway, and we can find out what happens at 5. Let's do that right now. Start by, well, we're doing a graphical. So instead of doing it with a table, we're going to do it with a graph. In this case, where exactly is 5? I could see that x equals 5 is right about here, isn't it? That's where it is. That point, it appears to me that point is 5, 3. Does that make sense? It's 5, 3? Sure it is. 5, 3. All right. So what is the limit as x approaches from the left? Let's get out the spray paint can and do some graffiti. Let's approach from the left. Here I come from the left. As I'm approaching an x value of 5, the y value gets to 3. All right, great. Let's get a different spray paint can here. As I approach it from the right towards the left, and I'm getting closer and closer to the x value of 5, the y value does get to, once again, 3. So guess what? The limit does exist, and it's 3. All right. A quick and easy check of that is obviously it's right on the line, too. The answer is right on the line when you put a 5 in there. And just if you wanted to double check and make sure it was 3, you could do that quick and easy by just going to the gear and typing in right now what happens at the place of x equals 5. And it says, oh, I got it right. I think I made a mistake here. 5. Say undefined. We'd have to put it in again. So come back like this. Yeah, there you go. There we go. Okay. So we're trying to turn this into a tab. There we go. When I put the 5 in, yeah, see, that's the issue. So if you look close, you can't see it, all right? But there isn't a value at 5 there. Let's zoom in, and I'll show you what I mean. Okay. All right, we assume it's kind of right here, you know. And you can't see this in Desmos, so we need to talk about this. You see it clearly in the illustrations. There's a hole there, you know, a hole. But you could tell looking as you approach from the left and from the right that it's supposed to be at 3. And unfortunately, we're not going to be able to see it looking at Desmos because Desmos can zoom in forever and ever, but it is ultimately a very tiny, infinitely unseeable hole. Show you what I mean. Get closer. See, we're trying to focus right there, but it doesn't appear as a hole, and it never will. So I need to tell you now, don't think you're going to be able to look through and find a hole. Why does it become a hole? The reason why it becomes a hole is because when you factor this part right here, it comes out with x minus 5 as one of the factors. And if x minus 5 is a factor and you put 5 in there, what do you get? You get an indeterminate form. It's not visible because the hole ultimately really is so very tiny that it's only for the specific value 5. There is a point at 5.0001. There is a point at 4.9999, but there isn't a point at 5, and you just can't see it, not with the biggest microscope. So it's abstract, and you have to kind of just assume it and realize it based on your knowledge of algebra. So what is the value when it's 5? The answer is undefined. There's no value. But you know, looking at the graph, if you come to it from the right and you come to it from the left, that it is 5, which brings us to using tabular analysis. So if you were going to use tabular analysis to do this, let's say we were going to approach it from the left. That means I'd have 4.9, and I have 4.99, I have 4.9999. Now look at my numbers. 9999999. Oh, it got to 3. It only got to 3 because it can't round anymore. You know, it can't show any more places. That's why I got to 3. But can you see that? I'm going to use some check marks to show. As I get closer, I'm 4.9, 4.99, 4.999. Look at what the number for y becomes. It was 3.05, then it's 3.005, then it's 3.0005, and here it's almost exactly 3. So as you approach 5 from the left, y does approach 3. Does it ever get to 3? No, there's no such point as 5, 3. We've established that, right? How about as I approach it from the right? How do I show that? Well, let's go above the number 5. What's above 5? Above 5 is 5.1, right? And then closer, 5.01, and 5.001, and 5.00001. Look at my numbers. They go 2.95, 2.99, 2.999. Now it's 2 point and all nines. See how it's approaching 3? So it's about as one thing changes, the other thing is changing in its own way. And if you can predict the way this should have changed, it should have got to 5. You could predict this should have got to 3, but it doesn't because of the rule of dividing by 0 is the idea. I hope that makes sense. It's kind of complicated, but that's the idea. The last idea associated with it here is, of course, the algebraic approach, which is if you factor the top and bottom of this, you're going to wind up with something that does ultimately cancel out. Let's show that math by going back to our lesson. All right. And in here, I'm going to go ahead and factor. I'll do it over here on the right. So the first one is x squared plus 2x minus 35. That, if you were going to factor, it will be x plus 7 times x minus 5. Why? Well, the reason why is because my end game is to find two numbers that multiply to make negative 35 and add up to 2. I'm looking right here to get that idea. Right here, they have to multiply to make this, and they have to add up to this. It's like a brain teaser. What two numbers multiply to minus 35 and add to 2? The answer is plus 7 and minus 5. And if I used FOIL right now and did first, outer, inner, last, I get x squared minus 5x plus 7x. See the 2x? And then I get, of course, my last, which is negative 35. Likewise, you could factor the bottom now that we're experts at factoring, right? So let's draw a line because this is a rational function. Isn't it rational? Yeah, why is it rational? Because it has a fraction in it. That means rational. It's going to be this time x minus 5, x minus 1. The reason why is because, again, I'm in a brain teaser, and I'm trying to figure out two numbers that multiply to make 5. Let me highlight that. But also add up to -6. Funny question, isn't it? Okay, two numbers that multiply to make 5 and add up to -6. The answer is -5 and -1. They multiply to positive 5, but add to -6. So here we have them. Very quirky math facts, but that's part of the reason why everyone struggles so much with factoring. It is really kind of like brain teasers a little bit. But can we see now what happens? Don't these knock out? Look, they knock out. And when they knock out, you could now rewrite the fraction with them gone. And if you plug 3 in there, 5 plus 7 makes 12. And then a 5 minus 1 makes 4. And then when you divide them, what do you get? 3. What's the answer? 3, right? So whether you do it by doing the spray paint can thing, coming left and right, that's graphical, right? Or you do tabular analysis, which is the number 5, we do 4.9, 4.99, or we do 501, 5001, etc. That's tabular analysis, approaching left and right, or numerically. Then you have algebraically, which is this action where you have factoring and you stretch things out and all that. That's the general idea of what today's lesson is about, is being able to conquer any and all of these kinds of limits. All right. Over here, if we plug in, oops, sorry about that. Over here, if we plug in -1 in here, we get the same situation. I'll leave that one for you to go ahead and play around with. It's explained in the textbook. And I know you read the textbook, but it's the same concept. It does not exist because of all those funny reasons we've discussed earlier. It's not the same coming from the left as it from the right, and different things like that. But one example is enough in this case, for example 8. Okay. There is one more last thing I'd like to share with you before we dismiss today, and it's the idea of finding limits as x approaches infinity. That looks a little bit like this. We really only know one thing about infinity when it comes to limits. And it has to do with division. Before we do that, we do have to do a little continuity. Let's talk about continuity. I'm sorry. We have to do continuity, and then we're going to go and do the infinity. But with continuity, I want you to remember the example of the word continuous. You know, math is all kinds of odd vocabulary words, but they do relate to what they mean in our speech and our language. For example, here's a great sentence. That baby screamed and cried continuously all night. Or that lawyer continuously haggled the person on the stand. Continuously means without a break. It means carrying on without a single solitary moment of a break. And most functions are continuous. There are no breaks. For example, take a look at this beautiful function. It just flows without any breaks, without any asymptotes, without any problems at all. It goes right through. There's no holes in it or anything like that. But notice right here we have a break. And right here we have a break. Here's another break. So when it comes to continuity, there's a lot of different ways to interpret continuity and to answer questions about continuity. The most cold and mathematical way to explain continuity is to use limits and vocabulary associated with limits. But what we can remember is if you're looking at a picture of a function, and you can graph any function with Desmos very, very easily, so you really should look at them. You see a picture of a function, and you graph it and it has an asymptote like this situation here, you should know that it is discontinuous there. The limit doesn't exist at that specific place where that asymptote is, that blue line where it doesn't touch. At 2, there is just no answer. What is f of 2? There's no answer. Maybe because it's over x minus 2. Maybe because of some reason in the story that it can never be 2 because of the application. Sometimes it's because of a worded reason like that. But in this case, the only thing that's not continuous is at 2. I can tell you what f of 1 is. I could tell you what f of 8 is. I could tell you what f of 37 is. I could tell you what f of -9 is. But there's one thing I cannot tell you, and that's why it's discontinuous. And where is it discontinuous? At f of 2 is the answer. So a lot of this isn't really even math as much as it's the language of being able to state things correctly, because you'll see in WebAssign when you do your homework, it'll be which of these statements is true about the continuity of h of x, and statements like I'm telling you. Here, the thing you would say is it's discontinuous at f of 2. In the cases of B and C, the whole point here is we have discontinuity because of special things in the graph, like division by zero or like piecewise situations. I'm going to clear these out so we could focus just on those for a minute. Take a look first at this graph. In this one, the function has on the bottom that pesky divided by zero issue. And of course, x cannot be 2. It should dawn on you quick and painlessly whether or not the factoring happens, that at x equals 2, you have a hole. Anytime you have any denominator with x that brings you to the idea of, oh, what if it's 0? And there's a number that would make it 0, that number is the hole, and it's discontinuous at that place. So if it was x minus 22, you could say, this function is discontinuous at f of 22, just like that. And it's the concept. Of course, you could draw a graph of it. You could say the limit doesn't exist. You could talk about limits if you want, but the bottom line is, if you see divided by something and the 0 issue comes up, it looks like a hole. All right. You can't see that in Desmos. So you have to look at the algebra for that. Whereas the last one you certainly can see in Desmos. Let's go over there for a minute. This one, we have a deliberate asymptote. You can see it. Desmos doesn't show you the asymptote, but you could see that there's a break, and there should be an asymptote. It's clear. Whereas here, we have a piecewise function. And in the case of a piecewise function, once in a while, you'll see that limits don't exist. And sometimes you'll see that they do. In this case, you'd have to say that it is discontinuous, particularly right there. The reason why is because the limit is not the same as the function value. Remember our first conversation today, which was about f of 2 versus the limit as x approaches 2. I'm talking about these two concepts, this versus this, right? They're both saying what happens at 2. The limit is what happens if you approach it carefully at 2. F of 2 is what is the answer. According to the formula or graph, what is f of 2? Here the answer is 4. F of 2 is 4 because of that dot up there. But the limit as we approach 2 is not 4. It's where that hole is. And that alone gives you another reason to say it's discontinuous specifically at 2. It might help to see something like this graphed in Desmos also to be able to answer the question of whether or not there's continuity there. All right. So that's continuity. Lots of fun, right? In review, let's not forget about polynomial versus rational functions. One of the reasons why we wanted you to be comfortable with those two ideas is because you can answer quickly and easily about continuity. For example, if you have any polynomial function, it's always continuous everywhere. So since you know what a polynomial function is, remember we talked about them like x squared plus x minus 9, or 5x cubed plus 2x minus 8. Anything you remember from 9th grade algebra that's not a fraction, has no cosine or sine or logarithm or square roots and crazy things, it's just a simple pattern, a polynomial function, they're all continuous at every value. So you could say, what is it continuous at 3? Of course it is. It's continuous everywhere. All right. But discontinuous functions show up when you see rational expressions and rational functions. So polynomial functions, that's easy. Continuous everywhere. But rational functions, discontinuous specifically based on whatever that denominator is. Even if you can cancel them out with factoring, it still is representing a discontinuity at that place. And that's important. So for discontinuous functions, here we have cases where you could go ahead and think about the concept of this denominator equals 0. And if you solve that little equation, let me write that in so that you can envision what I'm trying to say. Say the denominator equals 0 and solve that. You're going to get 3/2. And the way you say it is it's continuous everywhere except at 3/2. Or you could also say, of course, it's discontinuous at 3/2. Likewise, here, if you factor this, and remember this is again your difference of two squares, here's what the factoring would look like for that. X plus 2 there we go, x minus 2. All right, so if we factor it now, what if this equals 0? How would you do that? You might recall something called the zero property, where if you have two things multiplied and they equal 0, in other words, something like this, If you have two things being multiplied and the answer is 0, then it serves that it must be true that either A is 0 or B equals 0. This is something we like to call the zero property of solving. Different textbooks call it different things. I remember as a zero property. Most of the time they call it the zero property. But the point is, this is one of the many reasons why you would apply factoring to solve a quadratic or to solve a higher degree equation, is that if you can turn it into factors, like two things multiplied, then you could consider the first one being A and the second being B and solving two little equations. You probably remember doing this. This is an exercise they throw at you probably in the 9th grade in algebra class. So you solve x plus 2 equals 0, you solve x minus 2 equals 0, and you get 2 and minus 2. And of course, that is where it is discontinuous, because remember, you're trying to find those specific values that will make the denominator 0. If you forget, when you take your value of 2 and negative 2 and you plug it in right here, it does yield a 0 back to you, right? All right. Now, piecewise functions. Let's take a look at these functions here. Determine the values of x, if any, for which of the following functions are discontinuous. So this does require a little bit of being comfortable with how piecewise functions work. I would recommend researching a little bit, watch a YouTube video about it again, just to have a good grasp on it. But they are just ultimately pieces of other functions. I imagine when I teach it in the high school, I would take a scissor and cut a piece of paper and show that it's this piece and that piece here. So here we have two pieces and it looks like that. You could argue it's discontinuous at -1, of course, because that's where the funny stuff happens. You can see right there, it's a little fishy, right? It's like right here what happened, right? It's not continuous and smooth there. But here you'll notice, and I'm going to use my spray paint can again as illustration, you notice that there is a nice, even though there's a bump here, there isn't any place where I have any holes or any kind of asymptote. So this is continuous all over the place. There's no problems anywhere. I could tell you f of 2. I could tell you f of 0. I could tell you f of anything. Nothing is missing, right? So, and it's the same coming from the left as it is from the right for every point on the graph. And that's why it's continuous. So if you wanted to, you could type them into Desmos with using this special syntax with the fancy brackets, the colon and the comma, as you see here. So we have some more great examples for you to use when you're studying with WebAssign and getting your work done using Desmos. You can use these models for putting piecewise functions in when you need to. Okay, let's get to limits at infinity. When it comes to limits at infinity, there's one thing really only that we kind of know. We already knew this, okay, because we do believe that the limit as x approaches anything of a number is just the number, and we talked about that. So even if it's for infinity, so we already knew that. Likewise, when it comes to limits for infinity and negative infinity, it doesn't matter if it's negative or positive, it's still going to be that c, right? So if you're going all the way to the left or you're going all the way to the right, you're still just going to get C. Now, the next important thing is, and I want you to look closely at both of these. They are ultimately really the same kind of thing. They're trying to say that it doesn't matter what the top number is, because there was a rule that said that you could take the top number and make it a multiplier. That was in the past. Like c over x to the p is the same as c times 1 over x to the p. And if that be the case, c is a constant, so you can kind of ignore it and just put it in later. The point I'm trying to make anyway is the only thing that we do know about limits at infinity is the limit of 1 over x or 1 over x to the p, or furthermore, any number over x to the p for any p. Likewise here. And I want you to think about tabular analysis and how that would work. Let's do that for a minute, okay? Let's go ahead and take a look at Desmos once more. Desmos, I'm just going to go home and I'm going to go ahead and change this out. All right. I'm going to just give you the basic function y equals 1 over x. All right. Let's take a look at y equals 1 over x. And I'm going to use tabular analysis. So here's a table of 1 over x. Now, I'm going to let x approach infinity. Watch what happens. Let's let x be 10. We get 0.1. Let's let x be 100. We get 0.01. Let's let x be 100,000. I'm trying to approach infinity. I'm trying to get closer to infinity. Look at what happened. The answer is negative 0.0005, right? Look at how small the numbers get. In fact, if I really, really go, every time I put another zero, I get a little bit closer to zero. What's the point? Well, as x approaches zero, y approaches infinity, right? And if you say as x approaches infinity, y approaches zero, backwards and forwards with this kind of situation. Here, I'm going to use the spray paint again. Let's approach infinity, all right? I'm approaching infinity right now. Right now, in this way. Wait a minute. I'm approaching infinity right now. It's at 4. It's at 6. Look how much closer I am to 0. It's at 8. Look how much closer I am to 0. If I pull out like this, look how very close I get to 0 over here. In fact, you can even see on Desmos the values. At 100, I have 0.01. At 10, we have 0.1. I could keep putting numbers in and you'll see it just gets smaller and smaller. If we get closer to see it, and it isn't exactly 0. Look, it's not 0. But it's getting closer and closer and closer and closer. So as I get towards infinity, if I could possibly somehow reach infinity, which I can't, then this green line would touch the x-axis. And the point is the limit as x approaches infinity of this weird function 1 over x ultimately is going to be 0. So what is the limit? It's 0. Will it ever go beyond the line? Certainly not, right? Will it ever be negative? No, it will never be negative. It will never touch the line. It will get closer and even closer still, but never even touch it, much less pass it, which is why the very limit of it is 0. So we need to remember one really important idea. The limit as x approaches infinity of this is 0. Now, everything like that also is 0, like not just 1 over x, but 75 over x, 81 over x, any number over x is still going to be 0. And likewise, if I make it x squared or x to the third or x to the 10th, it only makes it get to 0 even faster. In fact, let's take a look at what that looks like. Here, I'll make it say x to the third. Look how much quicker it's getting to 0. 72 I have down here. So the point is, if you, instead of looking at the limit like it's a math thing in a box and trying to digest it, think of the idea. In a function like this, as you let the x value go closer to infinity, the result becomes closer to 0. The higher the x, the smaller the number down to 0. So the limit as x approaches infinity of 1 over x is 0. And any variation of 1 over x, like I'm showing you here, any exponents only make it happen even faster. X to the 10th is you're really going to be large exponents down there. All right. So if we can remember that, then we're able to use some really weird algebra ability to solve questions about limits at infinity. Like, for example, if we see right here, if we of course can't substitute infinity as if it's some kind of a variable, you can't insert it, but we can take each thing and divide it by x. That would look a little bit like this, and it's funny looking, so I'm going to write it for you. We're going to take each thing and divide it by x. We're going to have two x divided by x. Then we're going to have 1 divided by x. I'll give you some lines. I don't want them to be that thick. Hold on a minute. There we go. Okay. Right. And then that's all over. Bear with me, friends. I just want to make this really clear for everybody. Okay, now x over x. And then 2 over x. All right, now I know this is really funny looking, okay? But I need you to try to follow me on this for a minute, right? What I did was I took each of these things here, the 2x, the -1, the x, and the 2. And I carefully divided each of them by x. Look, see? And I made a very big, ugly fraction. I'm gonna let that sit there for a minute. I want you to look at that, right? This is how you handle solving limits at infinity. You take everything that you see in the fraction and divide it all by x, or by whatever the highest power is. Notice, just take a quick little glance in the future, you'll see here there's an x squared there. You'll divide everything by x squared for that one. Anyway, after you do that, what happens is all of these things become simple little mathematics ideas like this. And I'm going to come over here with it now. All right. Here on the top, I have 2x over x. That's just 2. And then I have -1 over x. Well, I know what 1 over x is. I figured that already. That's going to be my 0, because when I take the limit of that, I know that's 0, right? And then on the bottom there, I have x over x. It's like weird trivia. What's x over x? The answer is 1. X divided by x is 1. And then 2 over x. Now, take the limit of each of these things. Remember we talked about how we have important rules that give you the license to take the limit of each of the things in the sum, or if it's rational, you take the limit of the top and the limit of the bottom, right? So what we're going to do is take the limit of each thing. So let's do that now. The limit of this is 2. That's this idea, right? The limit of this is 0. That's this idea. The limit of this is 1. Once again, this idea. And the limit of this, again, is just 0, because in this case, the 2 is like the c, right? And ultimately, it kind of feels like, really more than that, it feels kind of like this is what's happening. As if you can just kind of slash these out, like they just disappear. The answer to this question is 2. It's 2 over 1, which is 2. And often these weird questions have simple numbers like 1/2. The answer is -1. You know, like usually they just boil down to something simple. And that's how you know you're on the right track with these calculus questions. You just get answers of 4 is the answer. And then you think to yourself, I think I got it right then. But my friends, make sure you always keep checking to make sure you have it right. You know what I mean? Let's just do that last one. For the last one, we would take each of those different things and divide by x squared. So imagine them all being divided by x squared. This would just be a 1, right? This would be the x squared, the 3 over x squared thing. Right? And then on the bottom, I have 1 over x squared. And then I have minus x over x squared. We'll just write that the way it is. All right, let's give them a line so that it makes sense now, right? All right, so if you divide each of these things here by x squared, you're doing it by x squared because the higher power is x squared, and you can't just do by x because you still won't be able to get an answer. In other words, if you just divide everything by x this time, x squared over x is x. So when you do the limit approaching infinity of x, there's no answer. But you have to just, the trick is divide by x to the highest power that you see. Here, the highest power I see is x squared. If you wanted to take Calc 1, they would give you a lot worse than what you're seeing here. They give you fractional powers and all kinds of horrible. But you know, here just the basic feel of it is divide by the highest power you see, which this time is x squared. So now you do it by x squared divided by x squared is the 1. 3 divided by x squared is that expression. 1 divided by x squared is that expression. And this expression right here, when I divide it, is going to be 1 over x, actually. I'll write that in. Right. So now what we'll do is we'll take the limits of each of them. That's not going to be hard because, like we said, we know which is which. The limit, of course, of this one is just 1. The limit of 1 is 1, right? The limit of this is 0, and that's because of this rule here. The limit of this is 0 because of that rule. And then the limit of this is 0 because of that rule also. So what does it mean? It means ultimately it's going to be 1 plus 0 on top, and then 0 minus 0 on bottom. Give us a fraction line. And what do you get? 1 over 0. What does that calculate to, friends? 1 over 0. 1 over 0 does not exist. The answer is does not exist. So once in a while, you'll get an indeterminate form. And when you do, and we talked about indeterminate forms, when you do, of course, you write does not exist. Okay. So I've given you a lot. I've given you a lot of limits stuff. That's a real lot. And you may feel a little bit overwhelmed. This is really a lot of information, but that's what happens in the summer class. There's a lot of stuff in the chapters we have to get through, and it might feel like it's kind of rapid. Don't worry, I put a lot of time in our schedule so that you have an extra day to study, and that and that we can talk and talk after class too if we need. And then the last thing that we got to talk about is limits at infinity and horizontal asymptotes. I'm just going to read this idea. I want you to just follow along with me. If you have a limit that you're approaching infinity and you get an answer like a b, and b is a constant, like for example 2 was in part A, then the line y equals b, or in this case y equals 2, is a horizontal asymptote. Horizontal asymptote means that it's a line that is horizontal, like this, that has a curve that gets very close to it but never touches it, like this. So maybe this one here is like x equals 2, and because the limit was 2 there. So that's what they're trying to say about how you can tell what the horizontal asymptote is when you do a limit at infinity of a rational function. The answer, whatever that number is, x equals, y equals, sorry, not x equals, y equals 2 is going to be a horizontal asymptote. All right. So when it comes to finding limits using technology, just to mention, in your textbook, they regularly use the TI-83 calculator. We are not using the TI-83 calculator. If you have one and you'd like to use it, you're welcome to use it, and you can do all of your lessons with it if you prefer. Desmos is definitely far more efficient, and if you find yourself in a position where you need a graphing calculator, you probably won't have one in the back of your pocket, but you will have a cell phone or a laptop, and you can go on your laptop right to Desmos. So I do recommend for your future that you get comfortable with the idea of using Desmos or something like Desmos as a graphing utility whenever it's time to come up with graphs. Here they're saying use a graphing utility to investigate the continuity of these functions. It's an exercise where you go into Desmos and try to type these things in using the syntax we talked about in this presentation, and you get images like you see here. Just as a brief mention, you should be able to notice, looking at a picture like this, that there is an asymptote right here. Likewise, you should know, looking at a picture like this, that there is an asymptote right here. Here, you should know that there is a break in continuity right here. And for something like this, since I can spray paint the whole thing, it's going to be continuous all throughout. All right, so you just want to, when it's time to use your graphing utility, if you're confused about which one was which, remember, you have this PowerPoint at your disposal here in eCampus. You could come or watch our video again and look at this once more and just remind yourself, oh yeah, that means it's discontinuous, to figure out where the asymptote is, or the break in the line is what it means, and so on. So you can come back here and use it as a model when you're doing your practice, okay? And we're just about through. There's one last little idea here we have to give. These are the general important rules that we discussed today about limits and continuous functions. There's another blue box like this that has to do with finding limits in chapter 9.1. That's important too. Please remember to come back here and look often at this when you're studying, if you're trying to answer questions as well. All right. So like I promised, I'm not going to keep you the whole time. I'm not a horrible mean math teacher. You're supposed to go at 6:45, but we're going to dismiss here. I'm going to stop our recording, and then after that, I'll open the floor to questions. Thank you, my friends, for paying such close attention to my lesson, and I hope you have a wonderful day.